Question number 3 asks you if you add 20 milliliters of 10 millimolar HCl to a 100 milliliter solution of 50 millimolar sodium carbonate, what will the pH be? All right, so for this one, so we're dealing with a weak acid, weak base here in sodium carbonate, and we're asked for the pH. All right, so the equation we're going to be trying to use here is a Henderson-Hasselbalch equation. So we're going to be trying to use, pH is equal to pKa plus the log of our concentration A minus over the concentration of HA. All right, so what do we have here? Well, we can look at figure 2.11 in your text and find the pKa value for carbonate. Now, carbonate is a diprotic acid, but we're starting off with the form that is lacking both protons, the 2- form of carbonate here. All right, so because of this, we're going to use the pKa value that's closest to that species, which is 10.2. All right, so we won't use the pKa value of 3.77. All right, so now we're after pH. We know the pKa. The only other things we need here are we need to know the concentration of the A- species of our carbonate and the HA species. Now, all right, we're basically given the concentration of our A- initially. So let me write the reaction here. So we have the HCO3 minus, right, giving up a proton to become, CO3 2 minus. Right, so this is our dissociation equation here. So our A- form is the carbonate, our HA form is the bicarbonate because it has the extra proton on it here. Now, we are given initially, we're given initially that we have 50 millimolar carbonate. So we're given the concentration of the A- initially, right? But we're changing up something here. We're adding in this strong acid. So if we have initial conditions and then a change, we're going to end up using an ice table. Right, so we have our initial I, our change E, and then the concentration at equilibrium, which is ultimately what we want, which is represented by the E row here. So initially, we don't have any carbonate, and we only have bicarbonate. And we have, so when making an ice table like this, I find it's very helpful often to not use molarity, but to use moles. So putting moles into the equation, I think, very often helps people out. So the question is here, I'm going to erase some of this stuff at the top. How many moles of carbonate do we have? Well, we have 100 milliliters. All right, I'm going to change everything to liters because it's going to help out our calculations. And 50 millimolar, so 50 millimolar, it's 50 millimoles, right, per liter. And we want to get rid of the milli term. So there are 1,000 millimoles in 1 mole. So if we multiply these together, right, we end up with, we have 0.05 moles per liter, right? All right, so start with that. So we have 0.05 molar bicarbonate. It's the same as 50 millimolar. All right, and we have 100 milliliters of that, which is the same as 0.1 liters. So 0.1 liters. All right, if we multiply these together here, we get we have 0.005 moles. All right, so that we have our initial concentration or initial amount here. We have 0.05 moles of carbonate. Now we're ready to calculate our change. So we're adding in a strong acid. So we assume the strong acid is going to completely react with the carbonate here, right? Because the H plus is over here. So it's going to react with the carbonate. So we're going to lose some amount of carbonate. but we're also going to gain that exact same amount of bicarbonate down here in our table. All right, the question is, how much are we losing and gaining? All right, so for this, we have to figure out how many moles we have of HCl. All right, well, again, we can take the 10 millimolar and convert it to molar, and we'll get that 10 millimolar is 0.01 molar. And remember, just as a review, molar means moles per liter. All right, and we'll multiply concentration times volume to get number of moles. So 0.01 molar times, instead of 20 milliliters, we'll convert it to liters. So it's 0.02 liters. Come on, pen. Sorry. Let me rewrite that. 0.02 liters. All right, and when we multiply these together, just want to make sure I'm doing the math in my head correctly. Yeah, so it's 3 zeros. So we get 0.0002 moles. All right, so we're going to lose that amount, so 0.0002, and gain that amount down in our table. Moles of, so we're losing that many moles of carbonate and gaining that many moles of bicarbonate. All right, so now we can solve for the equilibrium concentrations just by adding together these for bicarbonate. So we get 0.0002 moles of bicarbonate, which is our HA, and we have 0.0048 moles of our carbonate. So now we're ready to actually use Henderson-Hasselbalch at this point. All right, so let's pull up Henderson-Hasselbalch again. So we get pH is equal to the pKa value. Right here, pH equal to the pKa value, which is 10.2, plus the log of our A- concentration, which, by the way, is for the Henderson-Hasselbalch equation. If our A- and our HA are in the same solution, instead of using concentration of A- and HA in here, you can actually use moles of A- and HA. That's perfectly fine because the volumes would cancel out. So it's sufficient to say we have 0.0048 moles here of A-, and for our HA we have 0.002 moles. All right, so we do this math. The answer I'm getting here is pH is equal to 11.6. Right. So that is how you do problem number 3.